In this lesson, we're going to talk about magnetic forces on currents and also how it applies in electric motors. So, if a current carrying wire is parallel to a magnetic field, then the force on it is going to be 0. But if a current carrying wire is perpendicular to a magnetic field, the force on it is not 0. So if we have this current and a magnetic field going into the paper, it will feel a force going to the left. We can use the right-hand rule to find these forces. It applies to currents, but instead of having your thumb point in the direction of V, as we did for a charged particle, our thumb is now going to point in the direction of the current. And you can think about that as the current is really charged particles, and that's the direction that they're moving. We can also use, if you want to remember it as the I, we can use it's a bad finger, IBF. And your thumb goes the direction of the current, your pointer finger goes the direction of the magnetic field, and your third finger will tell you the direction of the force. So the magnitude of the force on the wire is given by this equation, and it's similar to the magnitude of the force on a charged particle in the overall format. Here, instead of V, we're going to have I. So the force on the magnetic force on a current carrying wire is equal to the current, which is in amperes, times L, which is the length of the wire. So the length of the wire impacts how much force it has, times sine of theta, where theta is the angle between the current and the magnetic field, times the magnetic field in teslas. We also have this equation on our AP2 equation sheet. And this equation is telling us that the magnetic field is found by the right-hand rule for forces. It is a cross product, and the cross product tells us to use our right-hand rule where we have I and then L, I and then B, and then that gives us our force. The L is not going to be a variable that we use to find the direction. All right, so which wire experiences a force to the left? So the best way to do this is to put your fingers in the right-hand rule position and point your third finger to the left. That will tell us the direction of the force is going to the left. And then use that to tell where is your thumb pointing. Your thumb will be the direction of the current, and your pointer finger will be the direction of the magnetic field. So which of these choices matches it? So if you put your third finger to the left, your pointer finger goes into the page, and your thumb goes up, so the answer is C. What about if I have two current carrying wires? Well, you can learn the general rule, or you can also figure this out. If you don't remember the general rule, you can figure this out by figuring the magnetic fields at each point. Well, the general rules are currents that are going in parallel wires in the same direction will attract each other. And currents that are going in opposite directions for parallel wires will repel each other. That's the general rule. But to figure this out, let's look at this example. If you use your original right-hand rule where you curl your fingers, you point your thumb in the direction of the current, and you find that the magnetic field for this wire is going to come out of the page and then back into the page. So it comes out at this point, and it's going to go. We want to see where how this magnetic field is going to affect this wire. So you take this magnetic field comes out of the page, and then at this wire it goes into the page. So if it's going into the page, we can figure the force on this wire by using our second right-hand rule, where we have our thumb going down and our magnetic field is going into the page, and that results in an upward force. We can also find the magnetic field from this wire, and if you use your right-hand rule, it will give you a magnetic field coming out of the page at the first wire. We use that coming out of the page with the current to find that the force goes towards the second wire. So if you do them step by step individually, you'll find that each of them goes towards each other. So we can also have a loop of wire. So let's consider a loop of wire with a current going through it, and it's going to be in a uniform magnetic field. So you can see from this picture our magnetic field is going the direction of the z-axis, where the B arrows are. We have a current going around the loop, and you can find the magnetic force at each point. You could find the magnetic force here, the magnetic force here, the magnetic force here, magnetic force here. I've already done it for you. What you'll find is the force goes up and down and left and right. So these are equal forces in the up and down direction and equal forces in the left and right direction. So the net force on this loop is 0. Based on our force, if looking at sum of forces, this loop should not be changing, should not be accelerating. There's another component involved here though. This is actually rotating on an axis. That means on the x-axis, this loop can spin. Well, as soon as you add an axis, you add the ability for torque. So the net torque on this loop is not 0. The torque will cause it to rotate. Torque is the rotational equivalent of force. So when we have forces that balance, they won't cause anything to rotate, but torque means that I have a force and it's at a radius from an axis of rotation. And then here I have a force and it's at a radius from an axis of rotation. So if I have torque, any kind of torque on something that can rotate, things can change direction if the torque isn't balanced. So in this example, the sum of forces is 0, so it doesn't accelerate. But because there is a net torque on the loop, it will rotate in a circle around. So this applies when we look at a simple motor, a DC motor and an AC motor. I have a current that goes through a loop of wire, and that loop of wire is sitting between two strong magnets. This loop is called an armature, the armature of the motor. It's on an axis and it is free to rotate. And then I have a current going through it. And you can see there's a battery right here, or a power source. The current makes this loop feel a magnetic force because I have a magnetic field and I have a current, and it leads to a magnetic force going up and a magnetic force going down. Those forces are balanced though, so it would not accelerate. It is the torque that's going to make this loop turn on its axis. The current will switch direction every 180 degrees to keep the armature rotating. On an AC motor, the switching of current direction is just how the electricity comes out of the wall socket for an AC current. For DC, there's a special component in your motor that allows the current to switch direction, and that will keep your motor spinning.